Biogas is helping Germany turn more than 150 million tons of manure each year into electricity, heat, and renewable gas right on the farm. From things that seem destined only to be thrown away, cow manure, organic waste, leftover food, and post-harvest byproducts, German farms collect, crush, mix, and pump them into giant digesters, then seal them completely, turning waste into a gas mine, right in the middle of the countryside. Yet behind this green model lies a paradox that could shake the entire agricultural industry. So how has Germany turned waste into energy? And why has this technology become the center of a major controversy? Join Terran Works as we explore it in today's video. Biogas did not begin with modern factories, but with the very phenomenon of swamp gas that had fascinated humans for centuries. When mud, dead plants, or organic matter decomposes in an oxygen-poor environment, it can produce a type of gas capable of catching fire. By the 19th century, this phenomenon gradually began to be transformed into technology. In 1859, one of the first anaerobic digestion systems was built in Bombay, India. And by 1895, biogas recovered from a wastewater treatment plant in Exeter, England, was being used to light street lamps. Today, biogas is understood as the gas produced when livestock manure, food waste, crop residues, or sewage sludge decomposes under oxygen-free conditions. The main components of biogas usually include 50 to 75% methane, along with CO2, water vapor, and small amounts of other impurities. Methane is the most valuable part because it can burn, be used to generate electricity, produce heat, or be refined into biomethane to partly replace natural gas. In Germany, this technology has developed so strongly that the IEA calls Germany the world's largest biogas and biomethane market, with combined production of around 329 pj in 2024. Biogas is developed in Germany not only because the country has a large amount of agricultural waste, but because Germany brings together three rare conditions at the same time: large-scale livestock farming, strong renewable energy policies, and the need to stabilize the power grid during its energy transition. Many countries also have manure, organic waste, and agricultural byproducts. But Germany is one of the few that has turned them into an entire industry. Since 2000, Germany's Renewable Energy Sources Act, or EEG, has created a feed-in support mechanism for renewable energy sources such as biogas, giving farmers and businesses an economic reason to invest in digesters, generators, pipelines, and gas treatment systems. As a result, biogas has become not only an environmental solution, but also a rural business model. The result is that Germany is now the world's largest biogas and biomethane market, with more than 10,000 biogas plants and around 87 TWh of biogas produced each year, far higher than many other European countries. Before cow manure becomes a raw material for biogas, everything begins with a tightly managed dairy farming system. As of May 2025, Germany had around 47,700 dairy farms and more than 10.3 million cattle of all kinds. The number of dairy cows alone in 2024 was around 3.6 to 3.7 million, showing that this remains one of the country's most important livestock sectors. On a modern farm, the cows are usually fed a mixed ration made up of grass, corn silage, hay, grains, and nutritional supplements to ensure they receive enough energy for milk production. On average in the EU, a dairy cow could produce more than 8,100 kilograms per year in 2024. So the daily demand for feed, drinking water, and care is enormous. That is why barns must be spacious and well ventilated, with resting areas, clean walkways, ventilation systems, and milking areas where hygiene is strictly controlled. At the same time, each mature cow can produce around 25 to 50 kilograms of manure per day, depending on its weight, diet, and whether the calculation includes solid manure or liquid slurry. For a farm with several hundred cows, the amount of manure generated can reach tens of tons every day. The biogas process on a modern farm usually begins right behind the barns, where manure and wastewater are collected in a controlled way instead of being allowed to accumulate naturally in the environment. On dairy or pig farms in Germany, liquid slurry is often directed through channels, underground pipes, or specialized pumps into an intermediate storage tank. Solid manure, leftover feed, bedding straw, or agricultural byproducts are also collected, stripped of large impurities, and sent to the raw material preparation area. Here, waste is not treated as something to be hidden away, but as an input energy source. Operators can mix liquid slurry with silage crops, grass, byproducts, or organic waste to create a mixture with more stable moisture and composition. Some systems also grind the material, stir it evenly, or check the feedstock ratio before loading it into the digester. This collection and preparation stage has a major impact on the efficiency of the entire plant, because microorganisms can only produce good quality gas when their food source is consistent, moist enough, and properly controlled from the very beginning. Once the feedstock mixture has been prepared and stabilized, it is pumped or loaded into the anaerobic digester, the central part of the entire biogas system. These are usually giant sealed round tanks, which from the outside look like industrial silos, but inside operate like a biological stomach, controlled by sensors and mixers. When the feeding hatch is closed, oxygen is almost completely removed, creating the right conditions for groups of anaerobic microorganisms to begin working. They do not break down the material in a chaotic way, but move through a series of successive stages, first breaking down complex compounds, then converting them into organic acids, and then transforming them further into simpler compounds, before finally producing methane-rich gas. Throughout this process, temperature, pH, retention time, and mixing speed must all be carefully monitored, because even a slight imbalance in the environment can cause gas production to drop sharply. That is why the digester is not merely a place where waste is stored, but the living heart of the plant, where energy quietly begins to take shape. As decomposition takes place inside the digester, biogas accumulates under the roof or in the gas storage chamber above the tank. But at this stage, it is still raw gas, containing methane along with water vapor, CO2, and certain impurities that can corrode equipment. Therefore, before it can be used, the biogas is directed through a piping system to be cooled, dehumidified, filtered of impurities, and pressure controlled. Once stabilized, this gas flow is sent to the CHP unit, where methane is burned to power an engine, turn a generator, and produce electricity for the farm or for sale to the grid. After biogas is used to generate electricity, the system does not allow the surplus heat to go to waste. The material left after digestion also continues to be processed. The solid fraction can be used as organic fertilizer or bedding material, while the liquid fraction is stored for irrigation and fertilizing fields. As a result, biogas does not only produce electricity, it also turns agricultural waste into a closed loop of energy and nutrients. But behind those clean, green biogas digesters lies a far from simple question. If bioenergy requires too much raw material, is agriculture still serving people first? Or is it gradually serving power generators? In Germany, corn silage once became an ideal choice for biogas plants because this crop produces a large amount of biomass, is easy to store, easy to ferment, and can generate a fairly stable gas yield. From a technical perspective, it is an almost perfect feedstock. But from an ecological perspective, the story becomes more complicated. When too many fields are converted to energy corn, the rural landscape begins to grow monotonous. Farmland is continuously exploited, and the diverse vegetation that once provided shelter for insects, birds, and small organisms gradually shrinks. The problem does not lie in biogas itself, but in how humans feed the system. A technology created to reduce emissions can become less green if it pushes agriculture to chase gas output while forgetting the balance of soil, water, and ecosystems. Biogas has contributed to Germany in a quiet but very practical way. First of all, it helps create a renewable energy source that is more stable than wind and solar, because biogas can be temporarily stored and then used to generate electricity when the system needs it. As a result, biogas has become a link that helps balance the power grid as Germany transitions to clean energy. Beyond producing electricity, many biogas plants also make use of waste heat from engines to warm digesters, barns, greenhouses, or provide heating for rural residential areas. Another important contribution lies in waste treatment. Manure, liquid slurry, agricultural byproducts, and organic waste are sent into sealed digesters instead of decomposing freely in the environment, thereby reducing odors, lowering the risk of water pollution, and capturing methane before it escapes into the atmosphere. For German farmers, biogas has also opened up a new source of income from electricity, heat, or biomethane, while creating jobs for technicians, drivers, and local service businesses. Therefore, biogas is not just energy. It is a bridge between agriculture, the environment, and the rural economy. The future of biogas in Germany will probably no longer lie in the race to build as many new plants as possible, but in how existing systems can be made cleaner, more flexible, and more closely connected to the real needs of rural areas. Instead of relying too heavily on fields of energy corn, farms will be encouraged to make greater use of manure, agricultural byproducts, and organic waste, feedstocks that are already generated every day. Older plants can also be upgraded to produce biomethane, use heat more efficiently, or operate more flexibly alongside wind and solar power. In particular, small biogas systems installed directly on farms could help reduce methane emissions from livestock, while generating electricity and heat on site. For that reason, the future of German biogas may not be flashy, but it will be more practical, turning organic waste into a stable part of a circular energy system. Today, the biogas plant model does not exist only in Germany, but has been deployed in many countries around the world. In Europe, countries such as Germany, Denmark, France, Italy, the Netherlands, the United Kingdom, and Sweden are strongly developing biogas from livestock manure, food waste, agricultural byproducts, and wastewater, with Germany still serving as the region's largest hub. According to the IEA, biogas production in the EU is heavily concentrated in Germany, while biomethane is growing in France, Italy, Denmark, and the Netherlands. Outside Europe, China and the United States also have many biogas systems, ranging from large livestock farms to wastewater treatment plants and landfills. India, Brazil, Indonesia, and South Africa are also seen as markets with great potential thanks to their abundant sources of organic waste. What these countries have in common is that they no longer see waste merely as a burden, but turn it into electricity, heat, or renewable gas for production and daily life. For thousands of years, modern agriculture has continuously exploited soil at an ever-increasing intensity to feed a rapidly growing global population. But behind these highly productive fields lies a silent crisis unfolding beneath our feet. Billions of tons of fertile soil are being lost every year due to overfarming, deforestation, desertification, and climate change. Many once fertile regions in Africa, South America, the Middle East, the Western United States, and Australia are gradually becoming hardened, nutrient-poor, unable to retain water, and nearly dead after decades of continuous exploitation. In some areas, topsoil that took hundreds of years to form is now being stripped away in just a few seasons of intensive mechanized farming and chemical use. At the same time, a larger issue lies in carbon. Normally, when plants decay or agricultural waste is burned, the carbon they once absorbed from the atmosphere is released back into the air as CO2 or methane, further accelerating global warming. Biochar, however, works in the exact opposite way. When organic biomass is heated in a low-oxygen environment, most of the carbon becomes locked within an extremely stable carbon structure that can persist in the soil for hundreds to thousands of years. This means that humans are not only restoring degraded land, but also transforming the ground itself into a vast planetary carbon storage system, helping slow down global warming, which is increasingly approaching critical levels. As the crises of soil degradation and carbon emissions continue to intensify, humanity has tested a wide range of solutions, such as chemical fertilizers, large-scale irrigation systems, and advanced carbon capture technologies. However, many of these approaches are either too expensive, highly energy-intensive, or only capable of addressing part of the problem. This is why scientists began turning their attention to an ancient secret hidden deep within the Amazon rainforest. There, they discovered extremely fertile dark soils known as terra preta, meaning black earth, existing within a tropical ecosystem that is otherwise naturally nutrient-poor. What makes these soils remarkable is that they have maintained their fertility for hundreds, even thousands of years. After extensive research, scientists realized that ancient indigenous peoples had unintentionally created this special soil by heating organic biomass, such as wood, leaves, and agricultural residues in low oxygen conditions, then mixing the resulting char into the ground. This is considered the earliest form of biochar, an ancient technology now being revived to address some of humanity's most pressing modern challenges, while also opening new pathways towards sustainable agriculture and a global circular economy. At first glance, biochar looks quite similar to ordinary charcoal. Both are black, lightweight, and produced by heating organic materials. However, the key differences lie in their purpose and internal structure. Charcoal is mainly designed for burning, so it is optimized for heat production and long-lasting combustion. Biochar, in contrast, is designed to live in the soil for hundreds to thousands of years. Under a microscope, biochar resembles a vast labyrinth filled with millions of tiny pores, forming a highly porous structure. This allows it to function like a natural sponge, capable of retaining water, holding nutrients, and creating an ideal environment for microbial life to thrive. More importantly, most of the carbon inside biochar is not released back into the atmosphere when it is used, unlike charcoal. Instead, it remains locked in the soil for extremely long periods. That is why biochar is not just charcoal, but is considered a tool for ecosystem restoration and future carbon storage, especially in the context of increasingly severe climate change. The journey of producing biochar begins with materials that much of the world once considered waste. On farms and in logging areas, millions of tons of dry branches, wood chips, nutshells, straw, and agricultural residues are collected instead of being burned in open fields. In many modern facilities, these materials are transported by massive trucks and fed into automated conveyor systems. High-capacity shredders then process the wood and branches into uniform sizes to prepare them for the next stages of production. Choosing the right feedstock is extremely important because each type of biomass produces biochar with different properties. Hardwoods typically yield more stable and carbon-rich biochar, while agricultural residues tend to produce biochar richer in natural minerals. This is why biochar is seen as a way to transform organic waste into a new resource rather than useless material. In some countries, utilizing biomass in this way also helps significantly reduce the burning of rice straw in fields, one of the major sources of air pollution and greenhouse gas emissions each year. After being shredded, organic materials still contain a large amount of water trapped within their cellular structure. If they are fed directly into a pyrolysis reactor, most of the energy would be wasted, simply evaporating moisture rather than producing biochar. That is why the biomass must go through a drying stage before thermal processing. In many plants, large rotary dryers operate continuously like thermal tunnels, where streams of hot air pass through slowly moving layers of biomass inside the system. As moisture is released, the material becomes lighter and more suitable for carbonization. At this stage, the moisture content is typically reduced to around 10–15% to optimize the efficiency of the subsequent pyrolysis process. Some modern facilities even reuse excess heat generated from pyrolysis itself to dry incoming biomass, significantly improving energy efficiency. Once the moisture level reaches the optimal range, the biomass burns more stably and produces more uniform, carbon-rich biochar, especially in large-scale industrial systems that operate continuously every day. This is the most important stage in the entire biochar production process. The dried biomass is fed into pyrolysis reactors with almost no oxygen, where temperatures can range from 350 to over 700 degrees Celsius. But instead of burning into ash like in a normal fire, the biomass slowly decomposes under heat. Inside the reactor, cellulose, lignin, and other complex organic compounds are gradually broken down, leaving behind a highly stable solid carbon framework. The process resembles the natural formation of coal deep underground, but accelerated from millions of years into just a few hours. The higher the temperature, the more porous and stable the resulting biochar becomes. Inside these sealed reactors, what was once branches or wood chips is transformed into a material capable of storing carbon for hundreds to thousands of years, with minimal decomposition even when buried in moist soil or exposed to natural microbial activity. In some modern systems, temperature and pressure sensors are also used to automatically control and precisely regulate the entire carbonization process inside industrial pyrolysis reactors. While biomass is being heated, biochar is not the only product formed. A large amount of combustible gases and vapors are also released from the organic material, including methane, hydrogen, carbon monoxide, and various volatile organic compounds. In modern facilities, these gases are not wasted. Instead, they are captured through closed piping systems and condensation units. A portion of the recovered gas is immediately burned to provide heat back to the pyrolysis reactor itself, significantly improving overall efficiency and reducing the need for external fuel sources. This ability to recycle energy makes many modern biochar systems operate like nearly closed-loop circular plants. Some technologies can also extract bio-oil, a type of liquid bio-based fuel that can be used in the energy industry. Because of this, many experts view biochar not only as an organic waste treatment method, but as a kind of carbon factory, where agricultural residues are converted into both usable energy and long-term carbon storage materials, delivering both economic and environmental benefits for many countries today. After many hours of pyrolysis, what remains inside the reactor is biochar, a lightweight black material with an extremely high carbon content. As it cools, biochar reveals its distinctive porous structure, resembling a microscopic labyrinth filled with millions of tiny pores. This structure gives it an exceptionally large surface area and a strong ability to retain water and minerals, far more effectively than many natural soils. Before use, biochar is often crushed into smaller particles or charged by mixing it with compost, organic fertilizers, or beneficial microorganisms to enhance its effectiveness when applied to soil. From this point on, what was once dry branches or discarded agricultural waste has become a material capable of restoring soil health, reducing fertilizer demand, and locking carbon away for extremely long periods underground. This is why many people refer to biochar as the charcoal of the future, rather than just another type of charcoal, especially in a world that is racing to find solutions for reducing global carbon emissions, while also easing pressure on land resources and agricultural systems that are already severely degraded in many regions. What makes biochar truly special is that it is not simply a type of black material used in agriculture. Once added to soil, biochar acts as a natural carbon reservoir capable of locking carbon away for extremely long periods, instead of allowing it to return to the atmosphere as CO2 or methane through normal decomposition. This long-term carbon storage capability is why biochar is considered one of the most promising carbon removal technologies in the fight against climate change. Some countries and companies have even begun investing in biochar as part of the rapidly growing global carbon credit market. Beyond that, its sponge-like porous structure helps soil retain water and nutrients more effectively, reduces fertilizer loss, and creates a favorable environment for beneficial microorganisms to thrive. In many parts of the world, from arid regions in Africa and the Middle East to overexploited farmland in the United States and Australia, biochar is being used to restore degraded soils, improve crop yields, and reduce the need for chemical fertilizers. Although biochar is considered a promising solution, its production still faces several significant challenges. First, building a pyrolysis system requires high initial investment in reactors, gas recovery systems, and temperature control equipment. This becomes a major barrier for small farmers and small enterprises to access the technology. In addition, raw materials such as wood chips, straw, or nutshells must be collected, sorted, and dried before being fed into the reactor. If the moisture content is too high, production efficiency drops sharply. The operation process also requires strict control of temperature and oxygen levels. Otherwise, the biomass may burn into ash instead of turning into high-quality biochar. Furthermore, biochar quality varies depending on the type of feedstock used, making standardization and large-scale deployment a major challenge. In many countries, the lack of transportation infrastructure and stable biomass collection systems also increases production costs over time. At a time when the world is simultaneously facing soil degradation, climate change, and a rapidly increasing amount of organic waste, biochar opens up a highly promising direction. From dry branches, straw, or agricultural byproducts once considered worthless, humans can now create a material capable of restoring soil, retaining water, increasing fertility, and storing carbon underground for hundreds to thousands of years. Although challenges remain in terms of cost, technology, and standardization, biochar is proving that sometimes the solution to the most modern problems comes from ancient human knowledge. If widely adopted, biochar could not only help regenerate degraded lands, but also turn the very ground beneath our feet into one of the most powerful tools for protecting the planet's future.